Okay, now let's talk about 9.17. This one we did in class also. It had a lot of things, so you got everybody a little bit confused. So let me go over it again, alright? So there is a flywheel, all the dimensions are here, 75 centimeters radius, mass of 40 kilograms, going around at 500 rotations per minute. And it is working like that at the time that I'm going to call T0 or T0. And it starts to stop because something broke down. It starts to stop, it starts to slow down. So that after 30 seconds, in a time that I will refer to as time 1, after 30 seconds, the angular displacement of this mass here is only 200 revolutions, and we would expect that if it's 500 RPM, it would be 250 revolutions after 30 seconds. So it has slowed down, and it has only gone around 200 revolutions after 30 seconds. So the question is, A, what is this velocity here at the end of this 30 seconds, all right? And then we'll talk about B. So this is A. So you're going to recall your equations from kinematics, but I'm going to replace your V's with omegas and your S's with theta and your accelerations with alpha. So I will write that, for example, the relationship between the velocities, the omega f equals omega naught plus alpha t, right? Or alpha delta t. We know this one. It's Vf equals V naught plus A delta t. All right. We want to know omega f after 30 seconds. We know omega naught. The problem is we don't know alpha. We know the time, but we don't know alpha or omega f. So we have a problem there, right? Another equation that we can use then is, let's keep going looking at our equations. We have that theta f equals theta naught plus W naught delta t plus 1/2 of alpha delta t squared. Oh, we're still in trouble, right? Because we still don't know. Oh no, we know this. Okay, sorry. Take that out. All right. So now we know the total displacement omega theta f minus theta naught. It's the 200 revolutions. We know the initial speed. We know the time. Now we can solve for the acceleration so that we can go back here and compute the velocity, the angular velocity we want to compute. So I'm going to use this to solve for the acceleration that I want to find, the angular acceleration, and then go back there to get my omega 1, all right? So let's find the acceleration. So delta theta equals omega naught delta time that multiplies the interval of time plus 1/2 of alpha delta t squared. Delta theta is the 200 revolutions. Omega naught is 500 RPM. Now we need to remember that this time that we'll use will have to be in minutes, because this is RPM, rotations per minute. So we don't want to put that 30 seconds, we want to put instead minutes. So this is times 0.5 minutes for the interval of time, plus 1/2 of alpha is what we're looking for. And again, this is 0.5 minutes squared. And then you're going to need to trust that I did the math. And once you rearrange this, you'll find that the angular acceleration is minus 400 revolutions per minute squared. All right. Now that we have the minus 400 revolutions per minute square, we go back in here and compute omega f. So I'm going to go back there, and I'm going to say that the omega after 30 seconds, which I called omega 1, is the initial omega, which was 500, right, RPM, plus, but the alpha is negative, so it's going to be minus 400. That multiplies delta t, which again needs to be in minutes, so it's 0.5 minutes. All right, and then you're going to get the omega 1 equals 300 RPM. So the velocity, it starts going 500 RPM, and after 30 seconds it's going at omega 1 equals 300 RPM. Okay? So this is A. B asks them, so I'm going to write it here now that we know this is 300 RPM. And I'm also going to take note of the acceleration we discovered to be minus 400 revolutions per minute square. I'm going to leave that there. And let's think about B now, right? So B asks, if the wheel continues to slow down at the same rate, if it doesn't get back to and start working again, then how long will it take for it to stop? So the question is, how long, what is the time, right, for the final velocity, which will happen, I'm gonna call it at time 3, because this was T0, T1, T2, excuse me. What is the, so that the omega at that time is 0. Okay, so remember again that omega f equals omega naught plus alpha delta t. Our question is, what's the time for this to go to 0? So this one goes to 0. Omega naught, you can choose whichever you want. If we choose the 500 RPM, the interval of time that we're going to find will be from the beginning, from T0. If we choose the 300 RPM, the interval of time that we'll find will be from there. So let's say, for example, that we do it right from the beginning. Then we'll have, this will be 500 minus, because the acceleration was negative, 400 times the time, times delta t. And then if you do that, you'll find that the delta t is 1.25 minutes after the initial time. Another way of doing it, just make sure, check that we did everything right, is the same equation, but now I'm going to start from the 300 RPM at T1. So I'll have, again, omega f equals omega naught plus alpha delta t. This will again go to 0, but now we are thinking about starting from the 300 RPM minus 400 is the acceleration, delta t is the time we want to know. Delta t now is 0.75 minutes. Which makes sense, right? Because the total interval of time is 1.25 minutes. And we know that there is 0.5 minutes, 30 seconds from T0 to T1, and 0.75 to the end. So everything is consistent. All right, so this is 9.17 for you. I hope that's more clear now.